Section 6.2. So section 6.2, we have optimization. Okay, so 6.2, we have optimization problems. And again, chapter 6 was the one where we learned a skill and then we use that skill in word problems. So this is really just doing word problems that have to do with absolute maxes and mins. It's going to be the same process for proving that something is an absolute max or min. Now, we had a worksheet on this, which outlined a process, but I'll outline it again here today. So, the first step, we're going to read carefully. We're going to label our givens and unknowns. Okay, the next step, step 2, we're going to sketch. And again, labeling is very important here. Our diagram. Step 3, this is the trickiest step. We need to come up with 2 different equations to model this situation. So we're going to write what we ended up calling a primary function. This was the thing to be optimized. Okay. And then we're going to use the secondary equation or the constraint equation and again, this was the one where the problem gives us info about. So this one problem would always give us a number here. Okay, let's slide this back over. So the problem gives us a number. So we're going to use the secondary equation to put the primary function into one variable. This is a 1 right there. All right, now, so that was just coming up with our equation. Again, the primary function is the thing that we want to optimize. The secondary or constraint equation is what the problem gives us a number about. In most of the cases, like the amount of fencing that I have to use or the amount of volume I need to contain. Okay, so the problem will give us a number. That number should always correspond to the secondary equation or the constraint equation. Okay, so step 4, we're going to find the domain. Okay, so oftentimes this is 0. Then we use the constraint to get a bound on the variable we want. I should say get an upper bound on the variable in question. And again, I think that this will become more clear as we do an example. Now, step 5, we find the critical points of primary. Step 6, find our absolute max and min. And step 7, we're going to get our final answer. Okay, here. Check your units. make sure that your answer is reasonable, right? So like if you have 300 feet of fencing, how would you contain 1,000,000 feet squared of area? That can't happen. Make sure that your answer is super reasonable. Okay, so that's that. Now let's do an example of an optimization problem. We know I love a good fence problem. So we have a couple of interesting ones with volume. Yeah, so I'll do a harder version of a fence problem. So this will be number 1 on the review. We need to enclose a rectangular field against the building. So we need to enclose a rectangular field against the building with a fence. We have 60 feet of fencing to do this. Determine the dimensions for maximum area. Okay, so my first step here, especially in these fence problems, is to draw out a diagram. So here, let's say that I have, this is my building. If you really want to get artistic, you can, define your building however you want, draw it however you want. But yeah, this is just a building. Now, I want to build a fence against that building. It's going to be a rectangle, so I don't have to worry about things too much. It's going to enclose some yard. I'm going to call this length X and these lengths Y and Y. Now notice, I don't have any fencing against the building. Okay, why would you put fencing against a building? That doesn't make sense. Okay, so it's just going to go up against the building. A couple of other variations that I could have thrown at you would be to say I want a pen to be divided into a couple different pieces. Things like that are pretty common. But yeah, so just be careful how you're labeling your graph and that you're accounting everything. So we want our primary equation. Now we know that we want to maximize the area. So because we want to maximize the area, our primary equation is going to be area, which is just x times y. It's just length times width. Okay. Now our constraint, what's the one number that we're given in this problem? Well, we're told that we only have 60 feet of fencing to do things in. Okay, so I only have 60 feet of fencing. So 60 feet is going to have to cover this length plus that length. Okay, I would rather you guys think of it as literally just adding up all of these lengths. You don't need to think about it in terms of a formal perimeter. Okay, so 60 is going to equal 2y plus x. Okay, I believe that thinking about it in terms of this way, in terms of just adding up what needs to be covered by those 60 feet, that is a much more manipulatable understanding of things, especially with how variations of fence problems go. All right, so I have my constraint equation, I have my primary equation. So what I'm going to do is I'm going to solve my constraint equation to get my primary equation in terms of one variable. Okay, so doing that, I see that I am just going to solve for x. I'm going to say that x is equal to 60 minus 2y. I'm going to plug that in here. So I see that the equation that I'm dealing with now is area equals, well, x is going to be 60 minus 2y times y. Again, I just plugged this guy. Let's grab a color over here. I plugged this guy in for x up there. All right, so I have my area equals 60 minus 2y times y. So this is going to be 60y minus 2y squared. And right now I'm just up to step 3. So this is step number 3, this is step number 2, this is step number 1 up here. Okay, so steps 1 and 2, I guess we can kind of consider in the same breath. All right, so I'm going to, I guess, box this in some sort of fancy color. Let's use blue. All right, now my next step is to find the domain, step 4. Domain. We know that x needs to be greater than or equal to 0. Why? Why does x need to be greater than or equal to 0? Because if x was less than 0, what does negative length mean? So in the previous steps, when I listed out the steps for optimization and I said that normally we mean that x has to be greater than or equal to 0, this is why. It's because normally we're working in a real context and having a negative value doesn't make sense. Okay? Likewise, we know that y has to be greater than or equal to 0. But I really just care about finding a bound on y. The reason is because y is the only variable that I'm curious about, that I'll need to be testing things for. In order to find this, all I need to do is say, okay, if x is greater than or equal to 0, this guy, then that tells me that 0 is less than or equal to 60 minus 2y. Again, this comes from our equation boxed in pink up here. So now I can solve for y, and I see that 2y is less than or equal to 60, or y is less than or equal to 30. Okay, awesome. I can do the same thing again for x, but we don't need to. It doesn't end up really helping us a whole lot. So now what I'm going to do is I'm going to find my critical point, step 5. A prime is equal to 60 minus 4y. Set that equal to 0 and solve. And we see that we get y equals 15. Now I do my chart. I've got 0, I've got 30 again. These guys come from my domain. Okay, I don't know how well the colors are coming through on the video, but we'll try it out and see if it works. And then we see that we have 15 over here, and that's going to sit right in the middle of these two. So 15 is our critical value. And again, these are y values, and now I'm going to plug these into a of y. If I plug in 0, I see that I get 0. If I plug in 15, I see that I get 450. And if I plug in 30, I get 0 again. And what do I mean by plug in? Where am I plugging these things in? Again, I'm saying a of 15, for example, is equal to, I'm running out of room, 60 times 15 minus 2 times 15 squared. Okay, that's how I'm getting this 450 down here. All right, so all this to say in my last line, I know that this guy right here, let's see if I can find another. This guy produces my max. And again, this tells me that y equals 15, x equals 60 minus 2y. So then x equals 30. So my final answer, the dimensions to maximize area are x equals 30, y equals 15 feet. Okay, that's my final answer there. Again, you could write 30 cross 15 if you wanted to use that notation, as I do on the review solutions. But yeah, so this is kind of how that problem goes, just step by step. And again, this is written on the review solutions. All right, moving on to section 6.3.